Hello and welcome to today's webcast. My name is Crystal and I'll be your event specialist today. All lines have been placed on mute to prevent any background noise. And please note that today's webcast is being recorded. If you would like to view the presentation in a full screen view, click the full screen button in the lower right hand corner of your screen. Press the escape key on your keyboard to return to your original view. For optimal viewing and participation, please disable your pop-up blockers. And finally, should you need technical assistance, as a best practice we suggest that you first refresh your browser. If that does not resolve the issue, then please click on the support option in the upper right-hand corner of your screen for online troubleshooting.
Welcome to today's webinar titled Leachables, The Hidden Dangers of Plastic, brought to you by Biotechniques and sponsored by Wheaton. Hello, my name is Patrick Lowe and I am a senior editor with Biotechniques. In this webinar, our speakers will describe their experiences with the problems that leachables from plastic labware can cause for drug screening assays and basic molecular biology reactions, as well as solutions for dealing with this issue. Following these presentations, there will be a question and answer session with the speakers, so please feel free to enter your questions into your webinar console throughout the presentations. We are pleased to have Lynn Rasmussen as our first speaker. Lynn is the supervisor of the High Throughput Screening Center at the Southern Research Institute and currently chairs a special interest group on labware leachables for the Society for Laboratory Automation and Screening. She will discuss how leachables can impact high throughput screening studies and how organizations are trying to address the issues surrounding plastic leachables. Lynn?
Thank you, Patrick, and thanks Biotechniques for the opportunity to participate in this webinar. Today I'm going to tell you about an incident that we had in our laboratory that we tracked down to a leachate. But first I want to go into what are we talking about. Next. In 2008 this paper came out in Science, and while it wasn't the first manuscript that was published on leachates, it certainly was the one that got leachates on the radar for most people that work in laboratories. The following year, the same group published another paper on bioactive leachates from lab plastics, which reinforced what they had published the year before, that leachates are real and they do cause problems in the laboratory. So next, at SRI, we were, I'm going to tell you about our experience. We were running a FRET-based assay in 1536 well format. It was a large screen, 750,000 compounds, so it spanned about 2 months. It had been running well with good Z's and a hit rate of about 0.5%, and then something happened. And it was initially observed that there were plates showing up in our screen that had large numbers of active compounds in some plates. These were not randomly distributed. The high number of positive wells were either located around the perimeter of the plate or concentrated in the center. The number of hits and their distribution was statistically extremely unlikely, so we investigated this artifact a little further. Next. On the left you see a normal plate from the screening run. This is the heat map. The purple color is the positive control, or what would be an active compound in the screen. Red is the negative control on the right-hand side of the plate, or an inactive compound. So you can see the normal plate has a few of the purple wells randomly scattered about the plate, and the artifact plate has a lot of purple wells concentrated at the top and the bottom of the plate. So it was clear that something was wrong, and the first thing that we did is what almost everybody else does. We took a couple of the plates that had produced good quality data and a couple of the plates that had produced poor quality data, and we ran them all together at the same time on the same day with the same reagents to see what was going on. This is really a quick way to rule out a lot of variables that can affect the screening campaign. In this case, though, the plates that had started out looking normal continued to look normal, and the plates with the artifact continued to show the artifact. So now we had to get into some serious troubleshooting. Next. So the troubleshooting strategy, first I'll tell you about the library. The library was provided to us in a 384 well polypropylene source plate configuration. When we received the library, we created a 1536 source copy by combining 4 384 well plates into a 1536 well plate in our laboratory. Now the 384 well plates were polypropylene, the 1536 well plate was COC. The artifact that we were observing in the screening run was coming from the 1536 source plate that was used to set up the FRET assay. So the first experiment we wanted to do was go back to the original 4 384 well plates that went into making some of these plates showing an artifact and see what the data looked like from those plates. Next. So the assay results from the 384 well plates obviously doesn't correlate with the 1536 well plate that was created from them. So it started to look like the copy of the library itself was a problem, and that really the only difference was the plates that they were in. Next. So more troubleshooting. Some more information about the compound library is it was supplied as part of the roadmap initiative. We were one of the screening centers in that initiative, and we were resupplied with the screening library annually. So we had multiple year copies of essentially the same compounds. They weren't 100% identical compounds in identical locations in plates from different years, but they were 90% the same compounds over time. The artifact was observed in a 2008 copy of the library. So our next experiment was to identify plates from the newer library, 2009, that contained 80% or more of the same compounds, and we engaged our IT department to query our database and tell us which plates from 2009 would be good comparisons for our problem plates. Next. So what we saw is the artifact in the 2008 plate was clearly not evident in the newer copy of the library, which we screened when we screened them side by side. So next. So further evaluation to determine if the artifact was related to the amount of time that the compounds were in the COC plate, we went in the opposite direction. We went to an older library, so this library had been in COC plates for a year longer than the library that was showing the artifact. The results of this were similar to 2009. So our conclusion was the artifact was not the result of compounds spending time in a COC plate. Rather, there was a lot of plates that we received in 2008 that was used to prepare this library that was leaching something into our compounds. So to determine the scope of the leachate interference, we were also running several other 1536 well assays in the lab, and we took some of our plates that had been showing artifacts in 2008, no artifacts in 2009, and we ran them in an FP assay and an alpha screen assay to see what the scope of the interference problem would be. Next. As you can see, the original FRET-based assay where we saw the artifact shows up in the 2008 copy of the library. The FP assay shows the same pattern. The 2009 copy of the library looks normal. The 2008 copy has a lot of false positives and is obviously an artifact. And then when we switch to a different endpoint technology altogether, which is alpha screen, we don't see any difference between the 2008 and the 2009 library plates. So it appears to be something that's interfering with fluorescent readouts, which is concerning because a lot of our screens use a fluorescent readout. Next, so what did it take to determine that the artifact was a leachate? So first we observed that there was an artifact, and with large screening campaigns, you monitor data over the course of the screen, and if there's changes in hit rate or data quality of any kind, you pick that up and follow up on why you're seeing changes in your data. The other way that you can observe these artifacts is if you're routinely running the same assay, like clinical laboratories do. They run the same battery of assays every day, and they run standards and controls, and if the data output from those is outside a pretty narrow range, then it again gets on somebody's radar to look into why things are changing. We had the resources to do the troubleshooting. So we had multiple copies of the same library. We had informatics to identify plates for comparison between different year supplies of the same library. We had multiple assay endpoints running in 1536 so we could compare them. And we had institutional financial support because anytime you start troubleshooting, it costs money to follow up on why things are not working correctly. Next. So what is the cost? In research, it's wasted time. You're wasting time repeating plates. You're wasting time troubleshooting. You're wasting time following up on hits that are false positives. You're also wasting resources, repeating things, and troubleshooting. And what concerned me most about this particular incident is the leachate was occurring in our compound library. So this entire library was basically considered useless after we had discovered this leachate problem. If you had put all of your library into these plates when you received it, your entire library would have been of no use anymore. In a clinical setting, the cost is a misdiagnosis. So you either treat a patient for something that they don't need to be treated for, or you may not be treating when it is necessary, which can have serious implications. Next. So in conclusion, identifying the problem as a leachate is hard. There's a lot of other things that can produce artifacts in screening, and you really have to dig and do some troubleshooting to rule out everything and track it down to a leachate. Identifying the actual leachate is even harder because now you need chemistry resources to analyze the leachate, identify what it is, and then if you're rigorous, you would resupply that compound in a pure form and put it back into your assay to show what the result was of that contaminant. And after talking to lots of people who produce the plasticware that we all use, controlling the production of the plastic that they get as the raw material and the resins that they get as raw material and the product that's being made from those is almost impossible to control for leachates and other low-level contaminants. Next. So there are a couple, there's a forum which is part of the, as relates to plasticware, and that's the Society for Laboratory Automation and Screening, the Special Interest Group Labware Leachables, which I chair, and we formed in 2012 to evaluate the scope of the problem. And we will be in Washington, D.C. February 8th, and we meet 8 to 9:15 in the morning. If you would like to join us, that would be great. And we're looking into, what's the impact and is there anything we can do, what can we do? We've had a number of discussions over the years with experts in different parts of the industry to try to get a handle on how we can address the leachate issues. When it comes to medical devices, drugs, containers for drugs, the FDA regulates that highly. And so what can and can't be used in medical devices and drug containers is strictly regulated. There's published SOPs on how to evaluate the rate and amount of leachate from the raw materials, and there's actually analytical labs set up to do this to help you with your FDA approval process. But all of this is very expensive and usually out of the reach of your average research laboratory. So thank you for your time and attention, and if you have any questions, this is my email. Feel free to contact me.
Great.
So I'm done.
Thank you, Lynn, for your presentation. Our next speaker is Dr. Engwee Chua, who's on the Faculty of Pharmacy at the National University of Malaysia. Dr. Chua will discuss how the choice of PCR marker tubes can affect the success of long-range PCR. Engwee?
Okay, thank you, Patrick. So in this webinar, I'm going to talk about the impact of selecting a suitable brand of PCR tubes on the success of long-range PCR. So let me introduce myself. My name is Engwee Chua, and I'm a lecturer working at the Faculty of Pharmacy, National University of Malaysia. So long-range PCR, as we all know, is an important tool with various applications in molecular biology. However, amplification of long targets exceeding 5 kb can be difficult because of several reasons. First, the likelihood of nucleotide misincorporation by Taq DNA polymerase is higher, and this can limit the final product size. Second, long templates are more susceptible to depurination at high temperatures, such as those employed for denaturation, which normally range from 94 degrees Celsius to 98 degrees Celsius. Third, the quality of input DNA is critical. Use of degraded DNA is likely to result in PCR failure. Various strategies have been adopted to overcome these limitations and make the amplification of long targets possible. CYP26 is an important pharmacogene responsible for the metabolism of many prescription medications. It is highly polymorphic. To fully characterize the common ethnicity-specific DNA variants in the gene, a number of long PCR assays are used. Because of the presence of pseudogenes with high degrees of sequence similarity, CYP27 and CYP28, long PCRs are typically performed to isolate the entire CYP26 gene in order to minimize sequence contamination caused by co-amplification of the pseudogenes. Also, some CYP26 polymorphisms are complex and involve exchange of large gene segments between CYP26 and the neighboring pseudogenes, as shown in the figure on the right. Such crossover events can result in the deletion of the entire CYP26 gene or the presence of a surplus gene copy. These polymorphisms can be detected by using long PCR assays. However, I have found the long PCR assays used for amplification of the CYP26 gene to have a low degree of reproducibility. Usually didn't work, but when it did, I was rather clueless as to why. Then it occurred to me that the only thing I may have done differently when the PCR worked was changing the brand of the tubes I used in my PCR assays. That led me to speculate the PCR tubes were inhibiting the PCR. So I started a series of experiments to confirm my suspicion. First, I compared 4 different brands of PCR tubes for their performance in the CYP26 and other long PCR assays. A PCR master mix was first prepared, and from this, 2 10 microliter aliquots was transferred into PCR tubes purchased from each of the 4 different suppliers, namely Fortitude, Neptune Scientific, Oxygen, and Labcon North America. The 2 aliquots were placed several wells apart in the same row in a thermocycler to account for possible positional effects. The PCR was performed according to a previously reported protocol, and the resultant PCR products were resolved on a 1% agarose gel. This figure shows the results of a few experiments that I had performed, ascertained the performance of different brands of PCR tubes in the CYP26 and other long PCRs. Overall, you can see that the use of PCR tubes purchased from Neptune Scientific produced clear inhibitory effects on long PCRs, confirming my previous speculation. In panel A, it is obvious that the long PCR efficiency was substantially reduced with the use of Neptune Scientific tubes in comparison with Fortitude tubes. In panel B, where 4 different brands of PCR tubes were compared, PCR tubes obtained from Neptune Scientific was clearly outperformed by those from other suppliers. The observation remains consistent even when the enzyme system was switched from kappa long-range hot start DNA polymerase in B to fusion hot start to high-fidelity DNA polymerase in C. The inhibitory effects of the Neptune Scientific tubes were even more prominent when the tubes were used to amplify a 13 kb fragment in another long PCR. There was no detectable product when the Neptune Scientific tubes were used. I suspected heating that occurred during thermal cycling could have induced the release of PCR inhibitory chemicals into the PCR mixtures, as there have been published reports that support this. Again, to confirm my suspicion, I added 10 microliter of water into the PCR tubes from the 4 suppliers. Long PCR was then done as usual. At the end of PCR cycling, the UV absorbance of the thermocycled water samples was measured. An increase in UV absorbance would indicate the presence of leached chemicals in the PCR mixtures. This figure shows the UV absorbance values at 220 nanometer for water samples thermocycled in the 4 brands of PCR tubes. For each brand, 2 10 microliter water samples were measured, and the resultant values were averaged. You can see that the water samples thermocycled in the Neptune Scientific tubes gave the highest UV absorbance value, suggesting that there were leached chemicals in the PCR mixture. The UV absorbance values obtained with other tubes were much lower. I repeated the experiment a few times and the trend remained consistent. I then tried to identify the leached compound by HPLC analysis. However, the result was inconclusive and the identity of the compound remained unknown to me. Despite this, I was still convinced that leaching had occurred to cause the observed increase in UV absorbance. It was quite possible that the leached compound was a colorant, as the Neptune Scientific tubes were colored and other tubes were not. I then tried other ways to extract the chemicals that could have leached into the PCR mixtures. To do this, I added 10 microliter of water into the Neptune Scientific tubes. The water was then thermocycled, transferred to 42 tubes. and left to evaporate in a laminar float cabinet. CYP26 long PCR was then carried out in the air-dried tubes. If a PCR inhibitory effect was observed with the use of the treated tubes, this could mean that thermal cycling had indeed induced leaching of compounds from the Neptune Scientific tubes into the PCR mixtures. These compounds were transferable to the 40 tubes, which would then become suboptimal for the long PCR assay. However, inconsistent observations were documented, as shown in panel A, where 2 unheated water samples were used as controls. An almost unnoticeable inhibitory effect was observed with the use of the 40 tubes treated with heated water samples. I couldn't replicate this observation in a second experiment as shown in panel B. So the result of the previous experiments could mean that the PCR inhibition was due to a different mechanism, namely adsorption of the reactions components in a PCR mixture onto the tube surface. To investigate this possibility, fragments was cut out from the Neptune Scientific and 40 tubes and added to the PCR mixture before thermal cycling. In another experiment, I also tried to reverse the PCR inhibitory effect by the addition of different amounts of bovine serum albumin, which could block the adsorption site or prevent leach chemicals from inhibiting the long PCR. As shown here in figure A, and contrary to what I speculated, addition of Neptune Scientific tube fragments into the PCR mixture did not result in an inhibitory effect. As shown in figure B, no rescue effect was observed with the addition of the bovine serum albumin. So overall, despite the observation of a clear inhibitory effect the Neptune Scientific tube had on the long PCR assays, the exact underlying mechanism was unclear. Besides, I repeated the experiment with a new batch of Neptune Scientific tubes and no inhibitory effect was observed, so batch-to-batch variation is another factor that should be considered. Nevertheless, my observation serves as a cautionary tale that long PCR could be sensitive to variation in reactions conditions. The take-home message is the choice of PCR tubes could be important in determining the success of long PCR. Colorless tubes are probably preferable as they may be less likely to leach chemicals into the PCR mixture and inhibit the PCR assay. Thank you for listening.
Thank you, Eng-Hui, for your talk. Our next speaker is Peter Rezik, who is the Global Marketing Manager for Wheaton Industries. Peter will discuss innovative solutions provided by Wheaton Industries aimed at solving the problem of extractables and leachables from plastic labware and protein loss due to nonspecific binding. Peter?
Thank you, Pat, for the introduction. Again, my talking points today is going to be focused on these innovative products, especially the anti-bind microplate product line, and overcoming leachate and sample loss issues. First, let me introduce to you Wheaton Industries. We are a 129-year-old company. So we have a long history of lab innovation, and we were founded by Theodore Wheaton back in 1988, and in part to provide the scientific community with essential glasswares such as bottles, vials, and other specialty glass products. Of course, as time progressed, the scientific advancement in both analytical equipment and testing has advanced as well, and Wheaton was there in the forefront providing elegant solutions to sophisticated problems. Continuing with the innovation legacy, back in 2015, we started to ask a question to our scientists and ask them, well, what are the biggest problems and issues that they are having with their lab consumables? And we came across two major issues that almost every scientist is facing. Number one is sample loss, especially protein samples, which are due to labware sample binding, protein adsorption, or non-specific protein binding to plastics. The second problems that we have, which Lynn and we have touched upon, was leachables and how they can cause imprecise results interpretation, and also how these leachables can interact with your samples, causing unnecessary and unwanted side effects. So we found these two problems, and really they were the inspiration of the anti-bind product line. So we went ahead and tried to find solution for these issues. So we're looking to provide labware that has two characteristics. Number one, have the least amount of leachables and extractables, and number two, allow for maximum protein recovery, especially at lower concentrations. So right now in the market, you have specialty plates that can provide that can solve one of these issues, but currently there are no solutions that can solve both of these problems. And really that was our endeavor and the quest to find the best labware out there too. So first, let's talk about our first issue, which is leachables or extractables. And really we started asking that question of where do these leachables and extractables come from. And we found that there are two major sources. Number one is the raw materials, and number two, production processes. So I'll take you through our journey of choosing the right material and also looking at the production processes to see how anti-bind was able to be manufactured in a way to eliminate or at least give the least amount of leachables and extractables. First of all, polypropylene. Really, polypropylene is the polymer of choice whenever we are talking about lab consumables. It's very versatile materials. It can be used in fresh food packaging, automotive industry, electro components, and medical applications, and many others. It is a downstream petrochemical derived from an olefin monomer, propylene, and it is added through polymerization reaction. Really, it is the compound or the material for choice for most labware, because it's semi-rigid, so it can be used a lot in lab automation. It has good chemical resistance, so it can be used in different lab assays and storage. It doesn't really interact too much. It can withstand very harsh chemicals. Good fatigue resistance. It's good for hinges and closure, so this comes in consideration. We're talking about centrifuge tubes or any equipment or any labware that has a hinge or closure, and also good thermal stability, so it can withstand higher temperatures. Now, polypropylene, right? So not all polypropylene are alike. Not everything is the same. And what we have found is that really the amount of leachables in solution is directly correlated to the impurities in the starting materials, starting resin. So we took a lot of effort and a lot of time to make sure that we start with the right material. So we evaluate the different resin types. Polypropylene resins, or the raw stock, can come as a homopolymer, block copolymer, or random copolymer. Of course, we went with the homopolymer because it has the lowest amount of extractables and better clarity than than others. We made sure we use the virgin polypropylene grade, which means the polypropylene it is not we did not use recyclable polypropylene, and then we also used medical grade polypropylene, which means it's low in extractables and leachables. Now, even though you can find a lot of companies offering these kind of resins, what we have found is the amount of impurities of the polypropylene resins or raw materials also varies from one company to the next. So we have evaluated different resin manufacturers, and we were able to choose one that gives us the least amount of impurities and one that is free for most extractables and leachables. Not only that, but now we have in place a system where we continue to look for and inspect our raw materials. So all the raw materials, the polypropylene resin is inspected via FTIR and GC, and this is to make sure that the raw materials that we use are of high quality and have the least amount of leachables. So that's number one. So we're happy about our raw materials or our choice of raw materials, and we believe that this is number one of tackling the big problems. The second step, or the second source of impurity of leachables, is going to be introduced during the manufacturing processes, and usually most of the labware is manufactured by injection molding, and really injection molding is just a method to obtain molding products by injecting plastic material molten by heat into a mold and then cooling and solidifying them. So as you can see here, here's a schematic of a molding machine, injection molding machine. Now this is just a picture. Of course, the one that we employ in the manufacture of anti-bind is a lot more sophisticated and a lot more complicated. But basically, in all injection molding, you have a hopper. That's where you put in your raw materials, and then after that, the cylinder, it gets heated. The plastic gets heated and get injected into the mold, and then once the plastic takes the shape of the mold opens and it releases the labware, and the cycle continues on and on. So this is an example of an injection molding processes, and really there was a lot of additives that are added in here to make sure that the manufacturing process goes as smooth or increases the output. So again, during the processing parameters, or during the processing of the injection molding, many companies use a lot of additives, and this is to increase the production speeds, which ultimately lower the manufacturing cost, and that's where you get a lot of leachables. And then secondly, some companies do not have fully automated system or fully automated process, and every time you don't have an automated process or a semi-automated process, you increase the risk of introducing foreign substance, and that can be introduced into the plate, and they can leach whenever you're doing your assays. Also, manufacturing these plates or labware in a clean room environment is very critical for having good leachable profiles. So let's take a look at the different additives that are placed with the plastics, and because these additives are the source or are the reason that we have a lot of leach hits in our profile. So as you can see, there are different types or different category of leach hits. For additive types. With stabilizer and processing aid are the most common ones that we've seen. We've seen leaching, but we also have plasticizers, which was basically additive to increase the plasticity or flexibility of the plastic material. We have anti-statics, which allow which additives that allow the polymeric material to disperse static electricity charges. We have coupling agents, and this is just to increase the interaction between polymer and filler if the company is using a filler. Coloring changing additives or pigment. So this is just coloring that you put in your product, or sometimes you put the color changing additives that if the material or the plastic endures or get exposed to heat or UV lighting, they change colors. So these will leach a lot, but we don't see these common in the labware. Okay, and of course antibacterial additives. So these are used to create resistance to microorganisms, so that the materials are protected from bacterial growth. So let's talk a little bit deeper about stabilizer, because these are the one that we see most in our leachate profiles. And basically, most companies, or most plastics, or most labwares will have antioxidants, and antioxidants is going to be placed sometimes in the manufacture of the resin and also during the manufacturing processes. And basically, they are these antioxidants are a type of stabilizer that protect the material during the processing and extend the material's longevity. And they're used to prevent degradation of the polymer that can result in loss of strength, flexibility, and color. So antioxidants really perform by eliminating the oxidation during and after processing when the material is exposed to any energy source. UV stabilizer is the same thing. They protect the materials from UV radiation exposed to extended period of time. And usually, if you do an extractable study, these would be organophos. XXX means there are a couple different numbers, 68 or 168 or what have you. And organox also is another antioxidant that is readily seen, that is readily leach from the labware. The second part, or the second type of additives that we seen a lot in leaching from labware is a processing aid, and basically they are divided into nucleating agents or lubricants and flip agents. So nucleating or clarifying agents, what they do, their function is really to increase the overall crystallization rate of the polymers. High crystallization speed, meaning that you will solidify the polymer at a faster rate when it's cooling, which means that you have a reduced cycle time, which means you're going to increase production, which means you're going to decrease cost. Lubricant is kind of similar, and is really used to improve the flow and the process material of the polypropylene resins. So what you will see with lower quality polypropylene labwares, you'll see the manufacturers put a lot of nucleating agents and lubricant and slip agents into their manufacturing processes, which create a huge headache to scientists, because all of these will leach into the solution. So that's why it's very important to look for high quality labware. So really, all of these additives are leached into solutions, and the way you look for them is we find a lot of there's going to be a lot of hydrocarbon impurities, aliphatics, hydrocarbons, long chain alcohols, aldehydes, mold release agents. They're going to be, it's a huge mess. They come out very easily. They leach out very easily in the presence of even water. And then also antioxidants and their oxidation products. So these are all the different impurities that you might see in your experiment if you're not using high quality, high purity labware products. With anti-bind manufacturing processes, we went to great extent to make sure that we start to modify and tweak all the processing parameters to make sure we're not introducing many additives that can cause a lot of leachates. That being the case, what we did is we have an anti-bind tech note number 2 that can be downloaded from the web, and really it went and examined the different extractables and leachables profile of anti-bind low protein binding plates, but I should say best-in-class low protein binding plates that's available in the market, and also 3 other standard polypropylene plates that are made by well-known, well-respected companies. The tech notes goes in details on the different experiment that we have done, but what we try to do is perform a very aggressive testing to determine the extractables and leachable profile for all of these plates and comparing to an anti-bind. So we did a chloroform extraction. So we took the plates, cryogenically ground them in a freezer mill to produce a high surface area, and then let them incubate in chloroform for 2 hours with an agitator and a shaker. And after filtration, we analyzed that extract via GCMS and LCMS. And I'm just going to show the data for the GCMS, but the full report is available for you to download and check it in more details. We also did isopropanol extractions. So we added isopropanol into the wells. We let it incubate for 72 hours. So this is a maximum time. And then again, we took the extracts and we characterized it via GCMS and LCMS. And again, I'm just gonna show the GCMS just for the interest of time. And the plate that we analyzed was anti-bind, best-in-class low-protein binding plates, which is competitor A, and then also conventional polypropylene plates as well. So as you can see, and the the two-ion chromatograms for chloroform extracts, you'll see that anti-bind is very clean, has the lowest impurities. This is competitor A, low protein binding plates. So these plates can offer protein can offer low protein binding capabilities, but as you can see, it leaches some of their compounds in here, which can be problematic if you are using a very sensitive or high throughput screening assays. Here are the other standard polypropylene plates, and you can see that most of them, all these impurities are coming off, are showing. And we are characterizing these peaks and these impurities, and hopefully they will be published in a different tech note. Again, with isopropanol extracts, you can see that not as many impurities or not as many additives or leached extractables came off, but still for some of the standard polypropylene plates, we have a lot of different materials that came off. So in summary, or the conclusion, whether we did the extraction using chloroform or isopropanol, or we evaluated via GCMS or LCMS, anti-bind plates consistently showed superior extraction performance when compared to the 5 other competitive plates, untreated plates or treated plates that are available in the market. Now, again, the full report, the full tech note is for you to download, and it goes into more details about the experimental procedures and also some of the results. So this is great. So we think we were able to tackle the first or the biggest issue, one of the biggest issue that the scientists are facing right now, which is extractables and leachables. But how about protein recovery, or how about sample loss due to protein interaction or protein absorption? And for that, what I'm showing you is really an evaluation of the standard polypropylene plates, best-in-class low-protein binding plates, and anti-bind technology or anti-bind plates, and looking at the protein recovery. And the graph that you see in front of you is that we took five different fluorescently tagged proteins. We measured the fluorescent intensity at concentration of 1.5 nanomolar and at time 0, and then we let it incubate for 72 hours. So that's really a long incubation time. And then after that, we remeasured the fluorescent intensity and then took the ratio between fluorescent intensity at time 0 and fluorescent intensity at time t, which is 72 hours. And then we calculated the percent recovery based on that. What you can see here that, after 24 hours, that the BSA or some of these proteins we lost all of them due in the standard polypropylene due to that protein adsorption issues, while best-in-class proteins, low-protein binding plates give us good recovery. With antibiotic technology, we're able to get 100% or for most of the proteins or around that area, and give us more recovery rate than anything that's available right there, in there. Now, if you remember, the question is, how are we able to have protein recovery, the high protein recovery, without having any leachate? If you remember, the best-in-class low-protein binding plates showed a lot of leachate in their extractables and leachable profile. And really, the answer lies into the plasma technology. So what we did is we employed advanced plasma treatment to our polypropylene to change the nature of the polypropylene. So as we know, polypropylene is hydrophobic. There's a lot of scientific articles out there that relates hydrophobicity with protein binding, and the more hydrophobic the surface is the more it will bind to proteins. And we know polypropylene is hydrophobic, so the challenge for us was how to change that outer surface and make it hydrophilic. And we went with the plasma technology. We added different functional groups that are covalently bonded to the polypropylene surface, and we allowed our surface to be a little bit more hydrophilic. And what we did, as you can see from the water contact angle for untreated polypropylene plate is 82 degrees. For our plasma treated one or anti-bind microplates, it's around 60, and that causes to have a greater recovery rate than anything in the market. So with that being said, really with the anti-bind product line, we were fortunate enough and we were happy to introduce to the market a plate that is able to both help scientists increase the recovery rate, especially when you're using proteins or some sticky molecules, and at the same time having that option without having any leachables and extractables. So we're very fortunate about that, and we think that a lot of scientists will find it very useful in their applications. With that, I can take any questions that you guys may have.
Thank you, Peter, for your presentation. We have now reached the end of our presentations. Thank you to all of our speakers for their presentations and to Wheaton for their sponsorship of this webinar. We now have some time for our presenters to answer and discuss selected questions from the audience. Unfortunately, Enri Chua is unable to participate in this question and answer session. Our first question is for Lynn. Lynn, have there been other reports of leachables from cyclic olefin copolymer labware that you're aware of?
Not off the top of my head, but if you do a literature search, you can come up with some references in the literature to where leachables are coming from.
Okay. Our next question is also for you. Are there any databases or registries that you know of for keeping track of reports of leachables from different plastic labware?
Actually, no, and that's one of the things that the special interest group with the SLAS has been looking into, is whether we can compile a list of potential contaminants and actually create a test plate that would include those contaminants so you could see if something was going to interfere with your assay. And if you saw interference, you might have an idea of what it was and where it might be coming from.
Great, thank you. Peter, the next question is for you. Can you provide more details regarding Wheaton's assessment of the extent of protein adsorption to polypropylene labware?
Absolutely. Actually, we have tech note number 1 that is published on our website that goes in great details about the protein recovery. And what we try to do is try to look for 4 to 5 representative proteins that are varied in molecular weights and hydrophobicity index, and see the recovery rates. So it's a fluorescent protein recovery experiment, and also take into consideration different time points. And we were fortunate to show that anti-bind microplates were able to offer maximum protein recovery than anything else in the market.
Okay, and the next question is also for you. If I have a choice to use HDPE, PS, PP, or PC, is there one that has less leachables over others?
That I don't know on top of my head, but I can definitely reach out and get that some information. I can check out the leachable profile for that and give you more information on it.
Great. Thank you. Lynn, the next question is for you. Is your SLAS special interest group pursuing any initiatives with industry to deal with the problem of plastic leachables?
We have had the discussion with industry about where contaminants are coming into the process from their raw materials or from their process itself. And we've had discussions about how to try to pin down whether it's a certain range of lots of plates or other, or tubes or whatever your potential material is that's leaching. And it's been very difficult. A lot of it is because of the way the raw materials are supplied to the manufacturers. A production run for a large chemical company making polypropylene is not what you and I think of as a lot, where it's a small defined group made out of a single source. So there's a lot of problems trying to pin down where the contaminants are coming from and how to monitor for them. But we would love to have people join us to kick that football around a little more.
Okay, great. And the last question is for you, Peter. One of the audience members asks, I wonder about polypropylene tubes and pipetter tips.
Absolutely. So since they're manufactured by the same resin, they go through similar processes of injection molding. Now, the amount of leachate in solution is going to be a function of time and heat. So the more time the sample is going to interact with the polypropylene tube or microplates, the more chance of the leachate coming into solution. So storage tubes is going to have a lot of big issues. Tips might not be as permanent as the tubes.
Great, thank you. Well, these are all the questions that we have. I want to thank all of you who have joined us today for this Biotechniques webinar on the hidden dangers of plastic leachables, and we hope that the webinar has proven to be informative and useful. I'd like to once again thank our speakers for their presentations and Wheaton for their sponsorship of this webinar. Goodbye.